So, hello everyone. Welcome to the inaugural session of the online GAP seminar series. And our first speaker will be Itai Dinur. Itai is currently affiliated with Ben-Gurion University and Georgetown University. He is a very well-known researcher with many contributions in various topics in cryptography. And today the title of his talk is Applications of Fourier Analysis in Security Proofs of Beyond But the Bound PRFs. And for the talk, I just want to remind the audience that you should keep your microphone switched off during the talk to avoid accidental background noise. And if you want to ask a question, I think today's talk will be quite interactive. So Itai will be taking questions during the talk. So you can raise your hands and one of us will spot. And I think Itai will also pause for questions, right?
Yes, I will do that. Yeah.
Yes, okay. So there will be, but when you're not asking a question, I would request you to keep your microphone switched off. Okay, so we can begin now.
Yes. Okay. So thank you very much for the introduction, and thank you for inviting me to speak. It's a great pleasure to speak at the seminar. So this talk will be in general about Fourier analysis and security proofs of symmetric key primitives. I just want to say before I go into the details of the talk. So most of the technical details are based on these two papers here. So if there is, if you're kind of watching this talk after, the recorded version, so you can look at these two papers to find all the missing technical details. But of course, if something is not clear during the talk, then please feel free to ask. Okay, so basic problem in provable security is to prove that a pseudo-random function is indistinguishable from a truly random function. And typically, we do this in two steps. So in first step, we model the main building blocks of the PRF by their ideal functionality. And here we kind of have an approximation error when doing that, and this error, so-called error, is bounded by cryptanalysis. However, in this talk, I will focus on the second step of this process. So in the second step, we have this idealized PRF with idealized building blocks, and we want to prove that it is indistinguishable from truly random function. And this is an information theoretic proof. Okay, so kind of a classical application of this is the security of counter mode. So assume that we want to encrypt a long message. So what we can do is we can break it into blocks, say M1, M2, etc. And we encrypt the first block as follows. So we draw a counter, some value. We apply a block cipher to it, and then we XOR the first message. We get the first ciphertext block. We increment the counter, apply the block cipher, XOR the second message, get the second ciphertext blocks, etc. Okay, so this is a very simple construction. So how do we analyze the security? Well, the first thing to do is to replace the main building block, the block cipher, with the idealized version, which is a truly random permutation. So let pi be a permutation from a space of n bits to the space of n bits. So we're going to assume it's a truly random permutation. And then we can bound the advantage of an adversary that makes Q queries to the scheme in using two terms. So the first term here is going to be the advantage of an adversary in distinguishing the block cipher itself from a truly random permutation. And the second term, and this is a computational term that's bounded by cryptanalysis. And the second term here is the advantage of an adversary that tries to distinguish this this truly random permutation from a truly random function using Q queries. And this second term here is bounded formally by information theoretic proof, and you can easily bound it by roughly Q squared over 2 to the n. This is the birthday bound that follows because a truly random function does not have collisions, whereas a random function, a truly random permutation does not have collision, whereas a random function, truly random function has collisions with high probability, and this is what you get. Okay. So let's be a bit more formal about the advantage. So let's assume we have some idealized PRF from, let's call it F, from some domain D, it doesn't really matter, and it outputs n-bit values. So we assume that we have an adaptive adversary A that makes Q queries to F. Let's call them I1 up to IQ. These queries can be adaptive, so the adversary can choose I2 after seeing I1, etc. And it obtains this output, F of I1, F of I2, up to F of IQ. And in information theoretic proofs, we can basically assume without loss of generality that the adversary is deterministic. Okay, and then we define the advantage of the adversary against F using this term. So it's the absolute value of the probability that adversary, when interacting with F, outputs 1, minus the probability when the adversary interacts with the random function that it outputs 1. Okay, so this is the formal advantage of an adversary. And now we want to bound the advantage of the overall, say, distinguishing advantage against the primitive F. So we just take the best adversary. So we take the maximal advantage of all adversaries that make Q queries. Okay, so now our goal is to bound this advantage. Okay, that's the goal, and that's kind of standard goal in symmetric key cryptography. Okay, so we have I mean the field is already quite mature. We have standard proof techniques for doing this. Game-based proof. We have the H coefficient techniques and some variants, and we have additional methods to do this. And typically, I mean, the standard proof techniques are what I call interaction-based proofs. So we bound the advantage kind of by directly analyzing the interaction of the adversary with the PRF. Okay, so we kind of monitor its queries, and we try to bound the advantage using all these techniques. That's how we in a very high level that's what we do. Okay, so now I want to kind of describe Fourier-analytic proofs in a very high level. So the goal now will be to bound the advantage of the against the PRF and the Fourier domain. So at a high level, this means that we're going to describe this advantage function using the Fourier coefficients of the PRF's output distribution or density function. Okay, and of course we'll see later what that means. And we will show that these coefficients are small, okay, and therefore we will get a bound on this advantage. So unlike these interaction-based proof, which kind of analyze the interaction of the adversary with the PRF, here the interaction is actually not analyzed in an explicit way. So it's kind of a maybe in this sense a different technique than the classical ones in symmetric key cryptography. However, I have to stress that bounding the distance between functions and Fourier domain is quite a common technique in TCS and mathematics in general. So in the general context, this is really something very standard. Although, like I said, in symmetric key cryptography, this is not very common. Okay, so let me give a brief outline of the remaining parts of this talk. So I will start by introducing constructions of beyond birthday bound PRFs and summarize the security bounds for them. Then I'll describe the basics of Fourier-analytic proofs and how they are applied to these PRFs. And finally, I'll conclude and give open problems. Okay, any questions before I move on? Okay, so I guess I mean most of the audience probably know. I mean up to now I just described a basic idea. So let me go into a bit more details about the construction. Let me first motivate these constructions. So many cryptographic primitives are based on pseudo-random functions such as encryption, MAC algorithms, etc. However, in practice, these PRFs are typically implemented by block ciphers, which are pseudo-random permutations that are secure only up to the birthday bound of Q, roughly 2 to the n over 2 queries, where n is the block length. Okay, and the goal of beyond birthday bound security is to obtain better security. So we want to design a pseudo-random function that is secure for for Q larger than 2 to the n over 2. And we're going to do this using pseudo-random permutations. Okay, so that's basically the goal. And kind of a standard example that shows that this might be necessary is we've already seen that is counter mode. And we had this for the advantage of the adversary, we had this birthday bound term. And in some cases, this birthday bound term might be quite concerning, especially when n is small, the block size is small, may lead to practical attacks. As shown by previous work, now, for when you consider AES, we have n equals 128, and this term is much less concerning. But if you want a high level of security, then you may still be concerned about this term. So you may want a higher security level. Okay, so classical PRF that achieves beyond birthday bound security is called the XOP, or XOR of permutations. Here we assume that we have two permutations, pi1 and pi2, from n bits to n bits. And given a query I, it's defined as follows. So you apply pi1 to I, you apply pi2 to I, and you XOR the results. Okay, that's how XOP works. Okay, and for the analysis, again, we're going to idealize pi1 and pi2. We're going to assume that they are uniform and independent permutations. Of course, in practice, they'll be implemented by a block cipher. Okay, and of course, you can then consider generalizations of XOP where you XOR together more than two permutations. Okay, so this XOP construction was first analyzed in 2000 by Lux. And there are, standard proof, so-called standard proof techniques applied to this PRF, and the best known bounds with this method is roughly Q squared over 2 to the 2n. Okay, and with the Fourier analysis, you can prove a stronger bound, at least beyond the birthday bound, which is roughly Q over 2 to the 1.5n. And this bound, you can show it's tight and better than the previous bound when Q is beyond the birthday bound, which is the range that we're interested in. In particular, if Q is roughly 2 to the n, then the advantage we get here, we plug in 2 to the n, roughly 2 to the n here, then the advantage is 1 over 2 to the n over 2. And if you plug 2 to the n here, you see that the advantage is constant. Okay, so you get, the more queries you make, the gap grows. And using, you can extend this results to actually prove tight bounds for XOP, the variants of XOP that XOR are different permutations. So this is a more general result. And you can also extend them to a multi-user setting, etc. Now, before I move on, I want to stress that actually, in fact, it turns out that for r equals 2, this bound, the optimal bound, was actually proved by Eberhard in 2017. His proof also uses Fourier analysis, but unfortunately, it was not very well known in this community. Okay, so we discussed XOP, we discussed the bound. So what is the application? Well, if you go back to the counter mode and you replace the block cipher with the XOP construction, again implemented, in the real world using block ciphers, then what you get is what you get here in terms of instead of the birthday term, you get a much lower term here. Okay, and this is nice, but the disadvantage here is that, as you can see here, in order to implement this, we require two independent permutations, and in practice, what you need is a block cipher with two independent keys, K1 and K2. So that's maybe not optimal. So we may want to kind of make the construction more efficient. And for this, let's consider a variant of the XOP, which I'm going to call SXOP. This is a name that I made up. It's not a standard name, but it's basically a single permutation variant of the XOP construction. So now we assume that we have just one permutation from n bits to n bits. And how do we define the output? Well, given a query I, which is now going to be a string of length n minus 1 bits, so we apply the permutation pi to I 2 times, but we domain separate the calls. So we basically prepend the 0 and 1. Okay, so the calls are domain separated, so we don't have the same input. And as in XOP, we just XOR the results to obtain the output. Okay, so unlike the XOP construction, there's a trivial attack here that we can consider. So observe that the outputs of these two calls, because the inputs are different, and pi is a permutation, then these outputs must be different. So the 0 string can never be output. The n-bit 0 string can never be output. On the other end, on the random function, it is output with probability 1/2 to the n in every call. And this gives a trivial attack with a complexity roughly q/2 to the n. And this is the kind of a lower bound on the advantage. And this attack actually turns out to be tight because there's a matching upper bound, and this was proved in some previous papers. Okay, so now let's compare XOP and SXOP. I mean, the two variants that we described. So we see that XOP has a better idealized distinguishing advantage compared to SXOP. On the other hand, it requires two independent permutations, whereas SXOP requires only one. So now it is natural to ask whether we can kind of combine these two advantages together and obtain the best of both worlds. And it turns out that this is possible. So I'm going to define another construction. I'm going to call it LXOP. That basically achieves the best of combines the advantages of the two previous constructions. So LXOP is going to use two calls to only a single permutation, and it's going to have an advantage which is bounded roughly by the advantage of the XOP construction, as if you were to XORing two independent permutations. Okay, so how are we going to define this construction? So first, we assume we have some function L from n bits to n bits. So it's going to be a linear orthomorphism. So what does this mean? It means that it will satisfy three properties. The first property is that it's going to be linear over f2 to the n. The second property is that L is going to be a permutation. And the third property is that we want the function defined by x XOR with L of x to also be a permutation. So we want these three properties to hold. Now, you can easily implement these three properties. There are various ways you can do it, and you can implement this very efficiently. So here is a very simple and efficient construction. So here's a Feistel-like orthomorphism, which is defined as follows. So in order to apply L to X, you split it into two words of the same length, like n/2. You XOR them, and then you XOR change their position, and you get an orthomorphism. So this is very simple to implement. And there are other variants which you can also that are also very easy to implement. Okay, so now how do we define this LXOP? Well, kind of the motivation comes from SXOP, where we had this, where we were XORing two domain separated calls to pi, but we had this problem that these calls were, the two outputs were never equal, and therefore this zero string was never output. So the goal is to defeat this attack. So how are we going to do this? We're just going to do the same, but the only thing that will change is that we're going to apply L to the second output here. Okay, that's the only difference. And it turns out that because L is an orthomorphism, then for every query, the output of LXOP, if we multiply as a uniform permutation, is uniform and 0, 1 to the n. So we basically defeated this attack. Of course, this is not a security proof, and this just shows you that the one marginals of LXOP are uniform, which is great, but that's still far from a security proof. To actually prove the security, you have to work a bit harder. But this at least gives you some intuition or motivation for defining LXOP in this way. Okay, so what is the application? Again, we go back to the counter mode, and if we replace the block cipher now with the LXOP construction, then we get the same, we get this smaller term here in terms of the advantage of the adversary, but now we're using just one key for the block cipher. Okay, so this kind of sums the first part of the talk, which discusses construction. So any questions before I move on to discuss proofs?
Yeah, Itai, I have a question.
Yes.
So it seems that your LXOP-based counter mode, it's kind of it's taking two block cipher calls to process each message block. So what about like considering the sync-based construction? I mean, it kind of reduces the
which construction? Sorry.
Sync ciphertext-based encryption, sync-based construction.
Yeah.
So yeah, I mean that will as you know, I mean that will reduce the overhead. Because you
okay, so in the paper, I describe another construction that is based on LXOP. It is based on the Iwata's PRF. So if you can mitigate this this amortized two calls per output, you can make it more efficient by implementing a variant of the PRF of Iwata. Okay, and you can, for example, what I show in the paper is that if you want to output two n bits, then you can do it, for example, with 3 permutation calls.
Yes.
Oh, and you get essentially the same advantage. You lose some factor here. I mean, but for example, for three calls and 2 n output bits, you get roughly the same. And yes, so basically you can generalize this to make it more more efficient to make it more efficient on average. Yeah, I guess this answers your question.
Yeah. Yes. Thank you.
Okay. Okay, so now let me move on to discuss proof techniques. So before before we'll apply the proof techniques to the constructions, then we'll discuss the basics of Fourier analysis that are needed for these proofs. Okay, so we'll talk about the Fourier analysis of Boolean functions. So I'll have kind of 5 slides that kind of describe basic properties that we need, and then we'll see how to apply them in the proofs. Okay, so given what I call the mask, denoted by alpha, so alpha is going to be a string of q words, each one of n bits. So this will kind of be our domain here, because the adversary, we assume it makes q queries, and it receives an input in this domain. And well, that's why we basically are going to always consider this domain. So given what I call a mask, we're going to define a parity function. So we'll denote it by chi I. It's going to be a function from our domain f to the n to the q to minus 1 and 1 to the set minus 1, 1. So we're going to define it as follows. It's going to be just a parity function. It's going to be minus 1 to the power, and here in the exponent, we have just the dot product of x and alpha, bit by bit. So basically, you think of this as just XORing the bits of x that are indicated by this mask alpha. That's why it's called a mask. And then we just move to the domain minus 1, 1 by raising minus 1 to this power. Okay, so this is basically a parity function. So that's one thing that we need. Another thing that we need is so-called an inner product. So we need so for functions f and g from f2 to the n to the q onto r, we're going to define their inner product as the sum over all x, f of x times g of x, and then we're going to normalize by the domain size, which is also equal to the expectation over x, f of x, g of x. So that's you can prove that this is an inner product. And the main property that we're going to use here is that these parity functions under the inner product form an orthonormal basis for the space of all functions from the domain to R. In more detail, what this means that the inner product of chi alpha and chi beta, so they're orthogonal if it is equal to 0 if alpha is not equal to beta, whereas the inner product of chi alpha with itself is equal to 1. This is what it means that these are form an orthonormal basis. And because the space is like the size of the set is exactly what you need to cover the entire space, then it is indeed a basis. And from this, from the fact that these are orthonormal bases of the space of function, it means that every function f can be decomposed as a linear combination of these parity function. And we're going to denote the coefficient of chi alpha by f hat of alpha. Okay, that's the notation that we're going to use. And this again follows directly by orthonormality. And again, by orthonormality, the way that we compute this f hat of alpha is by taking the inner product of f with the corresponding parity function chi alpha. And this is, we're going to just denote it. This f of alpha is going to be called the Fourier coefficient of f on alpha. Okay, so that's how the Fourier expansion of f is defined. So now let's see a few basic properties. So first, the chi of the zero mask on x. Well, you just, as you can see here, this is just the constant function 1. Okay, this is a constant function 1, and therefore the Fourier coefficient of f on the zero mask, you just take the inner product with the constant function 1, and what you get is just the expectation of f. So we have kind of you can kind of read off the expectation of f from the Fourier transform immediately. What about the kind of the second moment of f, the expectation of f squared? For this, we have Parseval's theorem, which tells us that the expectation of f squared is equal to the sum of the Fourier coefficients of f squared. Okay, and this again, I mean, it's a two-line proof. You can prove it using the orthonormality of the parity function. And this also means that we have a nice formula for the variance in terms of Fourier coefficient. So the variance of f, that's the expectation of f squared minus the expectation of f that squared. It's just the sum of all non-zero Fourier coefficients of f squared. You just subtract basically these two formulas, and that's what you get. We have also a nice formula for the variance. Okay, so so we're dealing with the security proofs here. So we'll actually be interested in distributions or densities. So let's define what is a density. So a function in our domain from f2 to the n to the q onto the positive reals is going to be called a probability density function if its expectation basically over the entire domain is equal to 1. Okay, so this is basically a standard distribution. It just normalized a bit differently. The way that the reason that we define densities and not distribution is just that it's nicer to work with Fourier analysis. It's nicer to work with the densities instead of standard distributions. If this were a distribution, we would be summing over Hicks and not taking the expectation. But that's just it's just some. We're just applying some normalization here. That's the only difference. In particular, the uniform density is going to be denoted just by a capital 1, not bold 1, just the constant 1 function. Okay, and then I mean, given a density, you can immediately get a standard probability distribution. You just need to normalize. So the probability, of obtaining x under the density is just mu of x, and then you need to normalize back to get a distribution. So you divide back by the size of the domain. Okay, and this is a valid probability distribution, because if you sum this over the entire space, you get 1. Okay, so these are basic definitions. Okay, and this is a very simple result that you can show that now we will be interested in Fourier and the Fourier coefficients of such distributions, and you can show that given the mask alpha, so the Fourier coefficient of mu and alpha, it's just the expectation of when you draw a sample from you of the corresponding parity function chi alpha. So it's basically the bias of the parity chi when you draw a sample from you. Okay, and this basically means that the Fourier coefficients of distributions have a nice and intuitive interpretation. So in particular, if you consider the uniform distribution here, if you draw x from the uniform distribution, then we know that all parities are unbiased on this uniform distribution. You just XOR uniform bits, then you get a bias of 0. And this means that the Fourier coefficient of all the Fourier coefficients on the uniform distribution vanish. They are 0, assuming that alpha is non-zero. Of course, if alpha is equal to 0, then because the expectation is then because this is a distribution and its expectation by definition is 1, then the Fourier coefficient of 0 is 1. Okay, so that goes for all distributions. Okay, any questions about this before I move on? Okay, so we're going to need 2 more notions. The first notion is statistical distance between densities. So a statistical distribution between 2 density functions is just half their L1 distance. That's a definition. And we have this following lemma, which says that the statistical distance between a distribution and a uniform distribution, it just you can bound it by half the variance of the distribution function. And as we saw a few slides ago, this variance has a very nice interpretation in terms of a very nice formula in terms of the Fourier coefficients of the distribution. So for example, if this is like the uniform distribution, then we know that all non-zero coefficients here of the uniform distribution vanish. So what you get here is 0. And so you get the statistical distance between mu and between the uniform distribution and itself is 0, which is basically what you expect. But if all these Fourier coefficients are small, you have like a small bias, then you expect this formula to be small. Then the distance here is small. Finally, we're going to need another very basic definition, which is the convolution. So the convolution of 2 functions from our domain to R is going to be denoted as follows: f convolve with g. Again, it's a function from our domain to R. And the definition is actually not very important for the stock. What is important is the following property. So if you let f to be mu1 and g to be mu2, and these are two density functions, then mu1 convolved with mu2 is also a density function. In order to sample from this density, what you do is you sample x from u1, you sample y from u2 independently, and you just XOR the result. Okay, so that's basically, I mean, this is what we need to know about convolutions. And the very nice property of convolution is that it interacts very well with the Fourier analysis. So we have this following lemma. So for every mask, the Fourier coefficient of f convolved with g on alpha, on the mask alpha, is just the product of the Fourier coefficients on alpha of f and g. Okay, so this is a very nice formula for the convolution in terms of the Fourier coefficient. Okay, so this is basically the base. This is what the basics of what I will need for the security proofs. So, any questions before we move on? Okay, so now let's go back to cryptography and reconsider the distinguishing advantage against the PRF. So recall that we have this idealized PRF f from some domain to f2 to the n. And we have this adaptive adversary that A that makes Q queries to F and obtains F of I1 up to F of IQ. And so again, this is what we saw previously. The distinguishing advantage against A is bounded by this is equal to this formula. We're going to take the disadvantage formula here. We're going to maximize over all adversaries that make Q queries. So now our goal will be to bound this advantage function in the Fourier domain. And the way that we're going to do this is as follows. So notice that A and F, of course, they define an output distribution density for F of I1 up to F of IQ. So this is a string of in F2 to the n to the q. Okay, so if we denote it, let's denote it by x. So how do we define this density? Let's just call it rho. It depends on A because it depends on the actual queries that the adversary makes in general. So rho A applied to X is just the probability that A obtains, gets the input X when querying I1 up to IQ. So that's a probability, and we're going to normalize it because we want to deal with density. So that's how we define basically the density. And again, it depends on A in general. And of course, it depends on N. And now that what we want to do is to bound the advantage in the Fourier domain. And the first thing that we're going to do is we're going to, if we look back at this formula here, then we're going to use a very well-known property that this term here can be bounded by the statistical distance between the density rho A and the uniform density. Okay, so this is a well-known result, and we're going to use it.
So Itai, sorry. So is this X is basically the response tuple that the adversary is supposed to get, right?
Sorry?
This X is the response tuple, right? This Q many responses.
Yes, right. That's kind of the responses. This F of I1 up to F of IQ is that what the adversary gets when it issues queries I1 up to IQ, right?
Okay, and here we are assuming that A makes adaptive queries, right?
In general, yes. This formula, assumes that A makes adaptive queries. That's why this distribution depends on A.
Okay.
That's why we have A here. Yeah.
I see. Okay, thank you.
Okay, so like I said, we want to bound this advantage in the Fourier domain, and the first thing that we're going to we're going to apply a standard theorem that says that this term here can be bounded by the statistical distance between rho A, that's the distribution that the adversary gets, and the uniform distribution over the same space. Okay, and now we want to move to the Fourier domain, and we had a formula for the statistical distance that bounds the statistical distance by this nice, expression here in terms of the Fourier coefficients of rho A. Okay, this is basically what I showed a few slides ago. Okay, so now we kind of have a formula of the advantage in terms of the Fourier coefficients of the distribution that the adversary sees, or the density function, if you want. Okay, so before I move on to discuss the details, let's give some motivation. Like why do we want to do this? So basically, what we're going to do is we're going to kind of bound this right-hand side here by showing that the Fourier coefficients are small. That these Fourier coefficients are small. So why is this useful? So this may be useful. I mean, this is not always useful, but it may be useful at least because as we will see, we can decompose these masks into related subsets so that Fourier coefficients of each subsets are related, and they can be analyzed independently. That's really important. I mean, in all Fourier analysis, the nice thing that you get is you can kind of decompose the function that you want into subsets and analyze kind of each subset independently. That's really important. And this gives you a better understanding of the function that you're trying to analyze, and may sometimes result in better bounds because when you're kind of trying to deal with this advantage function as a whole, I mean, it's hard to simplify it sometimes, and Fourier analysis sometimes give you a way to simplify it by kind of breaking it down into independent components. I mean, I'm not going to show this, but it turns out that if you have a very good understanding, it can give you a very good understanding of this advantage, and may actually sometimes give you, I mean, you can kind of read off the best attack from the Fourier coefficients. So this is kind of nice. So that's one reason that we may find this useful. Another reason, kind of a separate reason, I would say, like why this would be useful specifically in symmetric key cryptography. Well, we know that Fourier analysis interacts well with the group operations like XOR. We already saw an example using with the convolution, and we know that in symmetric key cryptography, we have a lot of we have constructions which apply a lot of these group operations. So it kind of seems that Fourier analysis, I mean, at least in some settings, would be suitable here. Okay, so that's kind of a basic motivation why Fourier analysis based proofs might be useful.
Itai,
Yes.
sorry, I have
Yes.
one question. Can you
Yes.
go back? So about this optimal attack, are you trying to indicate about so as you said, like these rho hat alpha, these are kind of the biasness from the uniform.
Yeah.
So
Yeah.
like the optimal attacks would be where like these are the heaviest ones, like when you have them.
So I don't know what is the optimal, like in general, like this is a very general formula, and if you can show, for example, so it will not, I mean, okay, so I wrote here that this can sometimes give you an optimal attack. I have a very specific example, and the example basically shows that. So it's a bit difficult to explain this without giving you the details, but essentially, the way that you do this is you partition this advantage function into components, and each component has a meaning. It's like a meaning, for example, for one component is that you just look, for example, at the one marginals. You just look at every single marginal of this advantage of these Fourier coefficients. Say you just look at the singleton queries, like you just look at every query independently. So that's kind of one component. And if you kind of find that this component is the heaviest component okay, then it kind of indicates that the best attack, what it does is it just kind of looks independently at each query of the adversary and tries to infer something. So these components have meaning, and if you find that there is a heaviest component, that this kind of hints towards a direction that that the attack should kind of make this component trying to maximize this component, and this kind of gives you an indication of how the best attack should work.
Okay,
So this is
sorry. So in this case, basically, the best strategy would be to make queries and look at all these singleton queries and try to find some.
Yeah, you're kind of trying to maximize the bias of every singleton query. Yeah, this kind of hint, this is kind of gives you a hint. I mean, so in the paper, I actually showed that. I mean, I showed this in more like more formally. I mean, in an example, it was actually based it is actually on the SXOP construction, where we see that when you XOR, for example, two values, then the zero value is never output, and you can actually infer the best attack from the Fourier coefficients of this construction. Because you see that the heaviest component is the one that on the one marginals of this construction. So again, this is I can't really show you all the details because it's a bit too much for this talk, but I just want to give you maybe motivation for this.
Thanks.
Okay. Okay, so now let's try to apply Fourier analysis to our permutation-based PRFs, to the PRF that we saw in the first part of the talk. Okay, so we have this formula for the advantage, and where rho A is the output density of the PRF that is given to A. Okay, so we're going to have two steps basically. The first step is we're going to reduce the Fourier analysis of the density function to, I mean, we have this basic formula here, and we're going to reduce it to Fourier analysis of the density function of sampling without replacement or random permutation. This is basically because all the construction that we discussed, the underlying building block is a random permutation. So we're going to move to apply some manipulation to move and analyze to kind of express this in terms of the Fourier coefficients of sampling without replacement. And then we're going to bound the relevant Fourier coefficients of sampling without replacement. And we're going to do this importantly by partitioning the kind of the Fourier coefficients into subsets. Okay, so that's kind of the basic strategy, and this is applied to all the constructions basically. The same strategy is applied to all three constructions that I described. Okay, the most technical part is going to be the second part. Unfortunately, I don't have time to really go into the details of this, and for this, I mean, you will have to look at into the papers. So let's start by the XOP construction. So we call it the XOP construction. That stores XORs two calls to two independent permutations. And here we notice a very nice property that these outputs that depend only the outputs of pi1 and pi2 that depend only on the previous outputs of the constructions and not on the actual query of the adversary. And this gives us a nice way to simplify the formula for the advantage. So we can actually we see that the XOP output, the output of XOP is actually independent of the adversary queries. So we can actually denote the XOP output density actually, distribution. But density, we can kind of remove the adversary from this formula. We can just denote by some, just call it pi, because the adversary, the queries of the adversary don't matter. So we just it just depends on the construction itself. Okay, now we have we kind of simplified the advantage function, and we don't have the maximal of the adversary anymore. We just have this phi here. Okay, so now the goal is to kind of express this in terms of the Fourier coefficients of the sampling without replacement. So let's define mu to be the actually the density. I would say it's more accurate of sampling Q elements uniformly without replacement. Okay, so now let's see how do we obtain a sample from XOP construction? How do we sample from it? Well, what we do is we XOR two independent samples from that are sample without replacement. Sample Q elements without replacement. And then by like what we saw before, just by definition of convolution, then phi is just again by definition is just two mu densities convolved with each other. This is again just the definition of convolution, and we know that we have a nice formula for the convolution in terms of the Fourier coefficients of sampling without replacement. And this, if you remember, then the formula says that it's just a product of Fourier coefficient, meaning that the Fourier coefficient of phi on alpha is the product of Fourier coefficient of mu and mu on alpha, which means that it's a Fourier coefficient of mu on alpha squared. And now we can plug this in to this formula, and we get this, again, very nice formula of the advantage of any adversary in terms of the Fourier coefficients of sampling without replacement. Okay, this is now raised to the power of 4 here because of this square. Okay, so now it comes down to analysis. We have to kind of understand how the random permutation interacts with the disparity function. That's what we need to do to analyze these formulas. And the way we're going to do this, as I hinted before, is we want to partition the mask here into what I call levels. And that's a very standard thing in Fourier analysis. I mean, the level, like I said, this partitioning comes again and again in Fourier analysis. So we're going to define the level of a mask alpha by the number of non-zero elements in F2 to the n. So kind of a mask, so the level is obviously an integer between 0 and q. So a mask of level 0 basically means that all the words are 0. And a mask of level 1 means that there is only one non-zero word out of the q words, etc. Okay, so we're going to partition the mask by level. And now we want to bound the sum here. So we, instead of summing over all non-zero alpha, we can have the sum from level k equals 1 to q of all, and then we have a sum over all masks with level q of mu hat applied to alpha to the power of 4. Okay, so that's now we've broken down the formula by levels. And now we kind of need to analyze the mass, the contribution of each level. So I'm not going to do this, but I'm just going to kind of give you an intuition why this is useful. So let's consider X, the sample from U, which means we draw Q elements without uniformly without replacement from F2 to the n. So we have these Q elements. They are drawn uniform. They are n-bit words drawn uniformly without replacement. However, if we look at every marginal, every word itself is uniform, right? Every xi here is an element of F2 to the n, and it's uniform. And we know that the uniform as we saw the uniform distribution, all the non-zero Fourier coefficients are 0. But this means that basically that if you look at masks of level 0, then the contribution is 0 because all the biases are 0. Okay, so this means that for mask of level 0, all the Fourier coefficients vanish. Okay, and this means that instead of going from k equals 1 to q here, we can actually go from k equals 2 because the contribution of level 1 masks vanish. Okay, and this is kind of gives you an intuition why this is useful. We're kind of looking at subsets of elements of a certain size, and it has kind of these are kind of related, and you want to analyze them together. Okay, so like I said, this notion of partitioning into the mask into subsets, and in particular into levels, comes again and again and again for Fourier analysis. This is kind of a very very basic, technique to analyze these to analyze these type of expressions. Okay, and of course, now it still have a lot of work to do. We kind of need to analyze the sums, and for this you can, more of the details you can look at in the paper. Okay, so now let's see how we analyze SXOP using kind of the same paradigm. So again, it's going to be the same template. So SXOP, previously in XOP, we were to XOR two independent permutations, but now we XOR two domain-separated calls for the same permutation. So it's going to be slightly different. So let's see how it goes. So again, we notice that that the outputs here actually only do not depend on the query itself; they only depend on the previous outputs. And therefore, once again, we can define distribution or density function for the output of the construction. Let's call it psi, and simplify this advantage formula. We can just bound it in terms. We can remove the adversary from this formula and just bound it in terms of the density of SXOP. Okay, so this is just the density of the output of sampling Q elements from SXOP. Okay, and now again, we want to formulate this in terms of the Fourier coefficients of sampling without replacement of this mu. So how do we do this? Okay, so let's consider a sample from SXOP denoted by psi. Okay, so the sample Z is, we can express it as X or Y. So now, before X and Y were independent because they were drawn from two independent permutations, but now it's the same permutation. So it's so the X and Y actually, distributed in terms of mu 2Q because we are sampling 2Q elements that are jointly distributed by sampling 2Q elements without replacement. So that's how the distribution here works. So it's no longer a convolution. Convolution would be if they were independent, but now they're not independent because they're drawn, all of them. All of these elements all these 2Q elements are drawn without replacement. So now we have to do something a bit different when we want to reduce the sampling without replacement. Okay, so I'll show you the formula. It's not very difficult. So let's do it. So the Fourier, so now we want to see what this means. The Fourier coefficient of psi on alpha, we want to see what it means in terms of Fourier coefficient of mu, of sampling without replacement. So by definition, this Fourier coefficient is the expectation when you draw a Z, when you draw a sample Z from SXOP, we're looking here at the parity, at the corresponding parity function, chi, alpha, and Z. Okay, but now we know that Z is equal to X or Y when where X and Y are distributed this way. So instead of sampling Z from psi Q, this is equal to sampling X and Y from mu to Q, just by what we've shown here, and now we replace Z with X or Y. And now we use the fact that this is a parity function, and chi alpha of X or Y is equal to chi alpha of X times chi alpha applied to Y. Okay, this is a very basic property of the parity function. Okay, and using properties of the dot product, this is again very simple transformation. This is equal to chi on the mask alpha alpha, so you double alpha. You kind of have alpha alpha, and you apply it to the mask X and Y. You just concatenate them. And here we have, again, the same X and Y drawn from U to Q. And this is, you look at this formula, and this is by definition, this is just the definition of the Fourier coefficient of alpha alpha on, of the mask, of the 2n-bit mask alpha alpha, not 2n, but 2q times n bit mask alpha alpha on the density mu 2q. Okay, so we have this formula. We have what we want, and now we just go to the advantage function, and we replace this these Fourier coefficients with these Fourier coefficients of mu, and now we basically did what we want. We replaced the Fourier coefficients of mu of psi with the Fourier coefficients of sampling without replacement. So now again we reduce the problem to bounding maybe a different type. It's a different structure of Fourier coefficients of sampling without replacement. Okay, so you can see here again, these are kind of some basic tricks that you apply, but everything at the end reduces to understanding the Fourier coefficients of sampling without replacement. And again, I'm not going to go to this in details, but you can, again, we partition this into levels. Unfortunately, like the first level here does not, I mean, the contribution of the first level is no longer zero because well, we know that the one marginals of SXOP, they're not uniform anymore. We had this attack. So here we cannot like make this simplification that we did for XOP, but we, I mean, we still need to analyze these type of formulas. Okay, and yeah, I'm not going to go into too much details here. I mean, there are a few technical details, but and then you can go on and go on to LXOP. That's the third construction that I described, which is a variant of XOP when you apply L here. And again, you can do the same trick. I mean, before we had this SXOP, we had this formula for SXOP with alpha alpha here. And if you move to LXOP, where you apply L to one of the outputs, then it's not very surprising. Then the Fourier formula changes accordingly. Okay, and again, this reduces to analyzing the sampling without replacement distribution, and yeah, it's just from here, it's just technical work. And it turns out that you can actually, okay, again, I'm not going into a lot of details here, and you can actually, I mean, reduce you want to bound sums of this form, and you want to bound them from SXOP and LXOP. It turns out that you can actually kind of infer these sums. You can bound them using the techniques that we developed for XXOP. You see the difference here, for example, if we take SXOP, is instead of in XOP, what we wanted is to bound sums here over all masks. And here we kind of bounding, we're not bounding sums over all masks, we're bounding sums over very structured masks. Like we have here symmetry, alpha alpha. And these are kind of sparser subsets that are kind of analyzed in principle, analyzed in a different way, but it turns out that you can actually, I mean, infer the bounds that we want from the sums on XOP, which bound I mean, the sums here over all masks. Okay, and again, details are in the paper. Okay, so I think I kind of maybe, I don't know, gave you maybe a general flavor of how this would go, but of course, I'm leaving out many technical details. So this is basically the last technical slide before I conclude. So any questions about this? Okay, so let me conclude. So I can summarize the advantages of Fourier analysis proof. So it can give you tighter bounds than interaction-based proof. And the way it does this is, yes.
I think Mridul has some question. Mridul, if you can unmute, maybe you can ask yourself.
No, I think this is just for the after the conclusion maybe. Anyway, so just the question is like, I understand the Fourier technique you have used. It doesn't. Well, we need that adversary's queries doesn't matter, right? So in the case when the adversary query matter, do you think the technique can be still useful? Like
okay, so you're kind of that's a very good question, because that's kind of the last bullet of this talk. Okay, so just wait 1 minute and we'll discuss.
Yeah. I actually meant for the after the conclusion. Yeah, this is.
Yeah. Okay. Yeah. So okay, so that advantages of Fourier-analytic proofs is that it can give you tighter bounds than interaction-based proof, and it gives you a fine-grained analysis of the PRFs output density function. You can obtain it with this, and sometimes it can actually allow you to find the optimal attack. And what we actually also saw that you can sometimes leverage this Fourier analysis in designing more efficient and secure PRFs, for example, XOP. I mean, this was kind of inspired by, I mean, the design was kind of inspired by, by Fourier analysis. That's how kind of I came up with this design. So yeah, I think it's kind of a nice example, and so let's so these are basically the advantages that I can see, and moving to open questions. So I think it's interesting to come up with more examples like this. You can leverage Fourier analysis to the knowledge that we gain from Fourier analysis to design additional primitives that have advantages over what we currently have. I think that's an interesting future work. And now we're going to Merdo's open question. So the main open question, I think, in this domain is to extend the scope of Fourier-analytic proofs. So the goal, I mean, ideally would be to be able to deal with adaptive adversaries when we did deal with adaptive adversaries, but we kind of, only in cases where the queries of the adversary did not influence the output distribution. So the goal is to kind of extend the scope to cases where the queries do influence the output distribution. And the techniques that we have for interaction-based techniques like H coefficients do not seem to work here because the queries are issued in physical space, but we want to analyze in the Fourier domain. So there's kind of a domain mismatch here. And to analyze this, this is unlikely to work. I don't know. I'm not saying it cannot work. I'm just saying that the standard techniques will not work. So what we will need here is to use analytic techniques, and there are techniques for doing this. And for example, in the TCS community, you can model the adversary as a decision tree, and then analyze the kind of the Fourier coefficients of this decision tree. And from this, you can actually infer bounds on adaptive algorithms in this model. Okay, so again, this will, I mean, if we want to do this, we'll have to kind of look at what other people are doing, and people have done similar things. And the question, of course, whether this would be applicable to symmetric-key primitives, that remains to be seen. But in general, there are techniques for doing this. So I mean, in TCS, I don't think they know what is, for example, H coefficient techniques. So what they're doing is just bounding the power of adaptive adversary and using other techniques. The question is whether these will be applicable in symmetric-key cryptography. That remains to be seen. And yeah, that's all. And I thank you for your attention. So again, I'll take any question if you have.
So hi. So may I ask one?
Sure, of course.
Yeah, sure.
Okay. Yeah. Thank you, Itai, for this great talk. So, at the initial of the talk, it seemed to me that Fourier technique is much more powerful than H coefficient one, because using H coefficient, we only reach to this, q square over 2 to the 2n bound for the sum of permutation, but your bound is kind of much superior than that. But then, in the very last slide of the talk, so H coefficient actually, incorporates the adaptiveness of the adversary, where this Fourier technique, as of the current scenario, when the adversary's queries does not influence the output distribution, then only you can kind of use this technique to bound the PRF advantage. So, do you want to make any comment on this?
Yeah, so that's basically the last thing that I said. We can't use the H. It doesn't seem that we can use the H coefficient technique, but we can use other analytic techniques. We need to model the adversary in a different way. And in TCS, the adaptive adversaries are modeled by decision trees. Okay. And there is a big line of work that that bounds the power of decision trees and some bounds on the Fourier coefficients of decision trees, etc. So we just need to, to do what they did, to try to use similar techniques here. I mean, they don't know. I mean, TCS, they don't know what is H coefficient. I mean, you say what is H coefficient to a TCS researcher, he has no idea what you're talking about. But they have a different set of techniques for analyzing adaptive adversary. The question is whether we can apply these techniques to efficiently analyze the constructions that are used in symmetric-key cryptography. That remains to be seen. But there are techniques, and there are, I mean, this is very heavily researched in the TCS community. I mean, again, in the symmetric-key cryptography, I'm not sure how many people are aware of this work, but there have been a lot of works on decision trees and in the TCS community.
I see. Thanks for this interesting direction that you have explored in this work. I mean, soon after we read this paper, we tried to apply this technique in bounding the PRF advantage for EDM, but then we failed because this convolution kind of stuff doesn't work for them. And you have also the adaptiveness of the adversary in the constructions as well.
Yeah, so like I said, I mean, it currently has this limitation with where it doesn't work with standard. There's a kind of a mismatch with the H coefficient technique, but again,
Yes.
I mean, you kind of need to expand your view here if you want to really extend the scope. I mean, you're going to have to do something a bit different, but. Yeah, I mean, whether it can be done, like I said, I currently don't know. That remains to be seen.
Okay. Thank you. Thanks, Itai.
No problem.
Okay, do you have any other questions?
Maybe just a speculative comment about this debate on adaptive, non-adaptive. Do you think, Itai, that we can do something, because in many H coefficient proofs, what we do usually is apply some, let's say, a universal hash function, and then based on the output, we say that certain bad events will not occur, and we bound the probability based on the universal hash bound. And then beyond that, it looks a lot like a non-adaptive game. So the input just has to be restricted in some sense. Do you think in those cases, maybe like on this conditional distribution, so suppose you sample a universal hash key with certain properties, and condition on that, the output distributions can be maybe analyzed using the Fourier analysis way?
Yeah, in principle, that might be possible. Yeah, so yeah, we of course need to look at the specific examples. Yeah, I can't say on top of my head whether something is possible or not, but yeah, it definitely might be possible. And I mean, another way to use, by the way, Fourier analysis is not. I mean, you can use them as tools in so-called interaction-based techniques. You don't have to have a completely analytic proof. Here we just bound adaptation directly by Fourier coefficients, and that's kind of a very clean transformation, and the entire proof is in the Fourier domain. But you can think of mixed proofs where you kind of use H coefficient or some other techniques, and then apply some Fourier tools in order to
Yeah, so as
in order to get some lemma or
module,
something.
yeah, sorry.
That's
Just as a
certainly
module,
possible.
yeah.
And by the way, it has been done, although in a slightly different context. For example, if analyzing generalizations of Evan Mansour, we have some Fourier analysis. It's a general. It's a big tool, and you can apply it in all kinds of settings. There are various ways in which you can apply Fourier analysis, and here I was focusing on a very specific type of proofs. But yeah, it's a very useful tool, and sometimes you can apply it in different ways.
Thanks.
Any other questions? Okay, if not, I think we can conclude the session. So thanks again for the very interesting talk. I think there are a lot of interesting directions to take from here, and it inspired some interesting discussion already. So, yeah.
Okay, thank you very much for inviting me. It was a pleasure to give a talk here, and I really hope that this that we will see some follow-up work on this.
Yes, let's hope some interesting follow-up work come out of this.